Hello. Today we're going to discuss 5.5 differentiation of logarithmic functions. Just like exponential functions in 5.4, the natural base plays an important role in here. The derivative of natural log of absolute x is 1 over x. So x can be both positive or negative in here, and in each case you just get 1 over x. Obviously x will not be equal to 0. So let's differentiate the function h of x equals nx over x. This is a quotient of two functions. We know the quotient root says the derivative of f over g is equal to f prime g minus f g prime over g squared. So we get the nx prime times x minus nx times x prime on the top and x squared at bottom. So that becomes 1 over x times x minus nx times 1 on the top. Simplify it, we get 1 minus nx over x squared for the final answer. Now, when the argument in the logarithmic function is a function f, then we have to use the chain rule. And we get the derivative of f of x equals f prime over f. For example, find the derivative of capital H equals ln x squared plus 1. We take the derivative of the x squared plus 1 on the top, and then divide by x squared plus 1, so we get 2x over x squared plus 1. One of the important applications of logarithms is the logarithmic differentiation. Sometimes we have some complicated functions like a product of multiple functions or quotient of functions. And then it will be much simpler to use the technique of logarithmic differentiation. So what's the logarithmic differentiation? We do 3 steps. Step 1, take the natural logarithmic on both sides of the equation and use the properties of logarithms to write any complicated expression as a sum of simpler terms. Step 2, differentiate both sides of the equation with respect to x. Step 3, solve the resulting equation for dy over dx. So let's do one example. Use logarithmic differentiation to find the derivative of y equal to the square root of 3x plus 5 times 2x minus 3 to the fourth. We know we can use the product rule to do the problem, but it will be quite messy. If we use logarithmic differentiation technique, it will be much simpler. So let's just rewrite function in exponents to get 3x plus 5 to the 1/2 times 2x minus 3 to the fourth. Step 1, take the natural log on both sides. So we got n on y equals n on 3x plus 5 to the half times 2x minus 3 to the fourth. We can use the properties of logarithms to separate the right-hand side into two terms to get n 3x plus 5 to the 1/2 plus n 2x minus 3 to the fourth. And we can put the exponent in the front in each term to get 1/2 times ln 3x plus 5 plus 4 times ln 2x minus 3. Now take the derivative of the equation on both sides with respect to x. So we get y prime over y. Remember to use the chain rule in here on the left. On the right side, we got two terms, and we have to use the chain rule again for each term. So we get 1/2 times 3x plus 5 prime over 3x plus 5 plus 4 times 2x minus 3 prime over 2x minus 3. So that becomes 1/2 times 3 over 3x plus 5 plus 4 times 2 over 2x minus 3. So simplify it, we got 3 over 2 times 3x plus 5 plus 8 over 2x minus 3. So let's try to combine those two terms by using the least common denominator, which is the product of the two denominators, 2 times 3x plus 5 times 2x minus 3. So we need to multiply 2x minus 3 on the top and at the bottom at the same time for the first term, and 2 times 3x plus 5 both on the top and at the bottom for the second term. And then we get the 6x minus 9 plus 48x plus 80 on the top. And the simplified, we get the 54x plus 71. And the denominator is just the 2 times 3x plus 5 times 2x minus 3. So now we can multiply y on both sides to solve for y prime to get 54x plus 71 over 2 times 3x plus 5 times 2x minus 3 times y. But y is equal to 3x plus 5 to the half times 2x minus 3 to the fourth. So we can do a little simplification, canceling some factors to get 54x plus 71 times 2x minus 3 to the cube over 2 times 3x plus 5 to the half. And you can rewrite the denominator as a radical, so that becomes 2 times square root 3x plus 5 at the bottom. So that's the end of this section.